So that's it for this 2D greens function example. Do we have any questions related to this 2D greens function example before we generate just the greens functions in a 3D problem? Okay, I don't see any evidence of questions, so let's go on. I think I'll just continue sharing my desktop here. So we'll go back to our local machine. And so we're going back to our good friend 3D Hex 8. And we're going to look at clean up things a little bit here. So now we're back in our terminal window, or our text editor example is 3D Hex 8. We're going to look at greensfunctions.cfg. So remember our pilot app file here. I'll just flash up momentarily. It set all of our basic parameters for all of our 3D Hex 8 simulations. So it would specify in our journal output. It specified where our mesh file was coming from. It specified our elastic properties. So we're using MatElastic as the default. We'll go through and we'll, if we have time here in a few minutes, we'll go through and we'll sort of mess around with some of these things to give you a better idea of, how to change parameters. And then we had our sort of a generic set of PETSI solver parameters. And so for our greens function specific case, we've put just a few of the greens function parameters here in our greensfunctions.cfg file. We're putting in our material ID for the fault, which is set to 10, switching over to fault cohesive impulses. Now here we're going to use 2 degrees of freedom for our impulses. This is a vertical fault, and so we're going to do both a horizontal shear direction as well as essentially the vertical shear direction. We say reverse slip, but this is a vertical fault, so there's sort of some ambiguity in terms of what component, which side of the fault ends up going up and which side ends up going down. So we basically just have to look at our results to see which one we end up with. But we can, if we were to do an inversion, we could be consistent about that in terms of making sure that we matched observations, and then we would see which side was going up and which side was going down. Amplitude of the impulses in a spatial DB. Now we're going to do, this file has a 2D variation of the impulse amplitude rather than just sort of a linear variation in the impulse amplitude. We're again using nearest interpolation. So let's quickly look at what that impulse amplitude looks like. So our data dimension is 2. We're specifying our data on a plane. We have 35 locations. And so what we've done is we've set up sort of the center of the fault to have an amplitude of -1. So that's turning our left lateral slip into right lateral slip impulses. And then around the perimeter of that, we're going to set the amplitude to 0. So around the edges of our fault, we'll have 0 amplitude slip. But then within the interior, we're going to be computing a slip impulses with an amplitude of 1. And we also have a step 21 file. These are sort of our very specific parameters to step 21. Because we have only one greens function example, we could have combined these into greensfunctions.cfg, or we could have moved those parameters over to step 21. We just chose that, we know we may end up with another greens function example in this directory, so we stuck some of our most basic parameters in greensfunctions.cfg. Total time is 0. This is, I believe, ignored in this case. Notice one thing to see is that Here we've used problem rather than time dependent because this is a Green's function problem. We could have put problem is the generic name of the component, or what we generally call facilities, and then the explicit cases are a time-dependent problem or Green's function problem. So time-dependent or Green's functions, that's FNS, as we've used in the past. Boundary conditions, we're going to put zero displacement boundary conditions on our favorite three boundaries, that positive x, and negative z roller boundaries. Again, we have one fault. Here we're not going to do subdomain output. We're just going to use the domain and points. So our points, we again use output solution points. Here's our Dirichlet boundary conditions. So on x positive and negative, we constrain the x and y degrees of freedom. On the bottom, a roller boundary condition, no vertical displacements. For the faults, all we need to do is specify, we've already specified our impulse amplitude, so it just has an ID of 10, the label fault. Hex mesh, where this is the fault, one dimension lower. Hex means Lagrange family of elements, so quads, lines, and hex elements are Fiat Lagrange. Cell dimension 2 for our quads. Output, we'll use HDF5 output. And so we're going to, our domain, as usual, step 21.h5. Our points, we add dash points. Here we're going to, we put our points for our Green's functions in this file Green's functions underscore points.txt. Here we're going to use a space dimension of 3. That's our coordinate system for that points file. And there, the units within that for the vertices are going to be in meters rather than kilometers like we've used in the past. Our fault output, in the info file, we're going to output our impulse amplitude. We want to check to make sure that the impulse amplitude, that patch where that is non-zero, is the area that we expect. And we're also going to output the area, which is essentially the tributary area for each of the vertices. So if we wanted to compute, say, the seismic moment, we could use these area values that are, remember we have an impulse amplitude of 1 at the vertex, decreasing linearly to 0 at the surrounding vertices. So this is essentially the, what you would call the area that would be associated with that, with the amount of slip for that particular vertex. We're going to turn off our state variable output. We still need to give it a data writer and a file name just to satisfy the validation. And then a mesh generation, as we'll discuss on Friday, we can run this problem in parallel, and in that case we want to write out the partition information. So that's step 21. Let's run step 21. So we run step 21 by first telling it that we want to do a Green's function problem. So pilot.problems.Green's functions and step 21.cfg. So here it's computing 40 impulses. And so it told us it was doing 1 of 40, 2 of 40, and so forth. And let's visualize what our Green's functions look like. So we need to get to the right directory, 3D X8 output. We're at step 21, so let's do point output and the fault output. So points, we want to display as points. Make them, make them nice and big. There's our faults. There's our faults. So there's our points are on the ground surface. We want to, let's show the displacement vectors for those points. Scale of 4,000. That should work pretty well. So there's our displacement vectors. We're going to show them. Let's color the points by displacement magnitude. On the fault, let's show the slip. Instead of magnitude, we're going to show X component. Let's show the surface with the edges. I think I'll show a few things from this side over here. So we'll see our displacement vectors, see the points colored by the magnitude, and see our slip. So this is our first slip impulse. Our second slip impulse, we notice, is in the vertical direction. And you'll notice that our X component of slip doesn't show it, but our Y component of slip does show it. So we're looping over the vertices, and for each vertex, we're going to first compute the horizontal impulse, then the vertical impulse, horizontal impulse, vertical impulse, and so forth. When you have a dipping fault, it's the lateral, left lateral component, and then the reverse / normal component. Vertical fault, it's essentially just a vertical slip. So there's X. So we see, here's our, that was our vertical components. Why am I not showing up? Slip. There it is. It looks like we have a, I'm showing that. The Y component. I think I'm just going to keep it on magnitude. So as I flip through here, you can see it's pretty easy to guess which ones are the horizontal components and which ones are the vertical components. When we have deep slip, a little harder to you can see the surface displacements are pretty small. There, when we have an impulse right near the observations, we get nice big vectors close to our impulse. Vertical, clearly a very different deformation. Deeper, smaller, more distributed. Very deep, less smaller displacements. And so you'll notice that we did not do any of the lateral boundaries because we said the impulses were going to be 0 there. So how would we know that that was indeed the case? We can load up our fault info file. So turn off everything else. Here's our impulse amplitude. So here we can see that we had an impulse amplitude of -1, but then 0 around the edges. And whether it flips, it's taken a quad and trying to color it. And so how it colors the quad, it can either color it the corners like this one over here on the lower left, or it can color it as this side over here on the right, but they are essentially the same. It's just a matter of how it chooses to color the linear interpolation within the rectangle. And our area, this is now independent of our impulse amplitude. This is the area associated with a vertex. So when we're in the interior, we have an area that corresponds essentially to the area of our triangle. So that's a million square kilometers, a million square meters, sorry, 1 kilometer squared. Then over here if we have a corner, we essentially just have a quarter of that. And then on these edges are essentially the area is half that of what it would be for one of these interior. So this allows us we could take the slip at all of these points, an inversion multiplied by the area, and get an idea for the seismic potency. To convert that into a magnitude, we need a shear modulus. So then we would query our spatial database of material properties to compute the shear modulus to get the moment magnitude. And there is a utility script called pilot, I think it's EQ info. It's documented in the manual that you can run that'll compute your magnitude, average slip, and so forth for any simulation. You do need to give it HDF5 files, and it'll look at your fault file at a particular time step, look at your material properties, and compute the statistics and information about how much slip, as well as what was the moment magnitude associated with that slip. So that wraps it up for this 3D greens function example. Are there questions about the differences between, say, 2D and 3D greens functions or greens functions in general? It looks like we're getting a question from Eric. So while we wait for Eric's question, my intention is the rest of this session, we can run through a couple examples. I think one area that users often have a little trouble is what to do when they encounter an error message and diagnosing an error message. So I'd like to run through a few examples where I intentionally put in a typo to cause something to fail, as we did a couple days ago. So the question is, how would you do greens functions for two connected fault patches? Do you need to generate them separately and pilot as two problems, then combine them in an inversion? So if we had two independent fault surfaces, such as, say, so the first, there's multiple ways to handle this. If they were the same fault surface but sort of separated, you wanted to do inversions for one piece of the faults separately. You wanted to sort of only do greens functions over these two separate patches on the fault. Then you could set up your impulse amplitude spatial database and have two patches of non-zero amplitude. And so by adding in more points in your spatial database to give, sort of identify these two regions of slip, you would then end up computing impulses for just those two regions and not the region in between. Now, if you have, say, two non-connected fault surfaces, such as, let's just say, the San Andreas faults and the San Jacinto faults, then you would have to do two separate greens functions generations. So you would first use your San Andreas fault as your fault with applying impulses, and then you do another greens function simulation with impulses on the San Jacinto fault. And then you could then combine the output from those two, so you'd have, instead of just getting the responses from one file, you get the responses from two different files, and then you do the inversion by combining those two into a single inversion. So you can generate your greens functions across, a number of simulations for different faults, and then take your Python script, and in our Python script, you notice how we were doing things like stacking values and using sort of the ways where you combine arrays into a larger array to assemble our sort of global, if you want to call them, vectors and matrices to do the inversion. And so you did the same thing in terms of where we had sort of multiple components of displacements. We'd have multiple components of displacements from multiple sets of greens function calculation and just assemble them into a larger inversion. Any other questions? Question from Robbie: if there's a bias in a fault mesh, will it cause a problem when calculating the area around a vertex? So if you have I'm not quite sure what you mean by bias, but if you have, say, variation in discretization size, then that is taken into account when computing the area. So say we have a finer mesh up here in the corner, then the area associated with those vertices would be smaller, but we have more vertices. And so it is, it knows how to take into account the variation of the discretization size when it computes the area. And it's doing this in a rigorous sense, and it's using, it's not assuming anything about the discretization size. It's actually looking at the mesh and computing the area.